Imagine standing at the base of a tower so tall that its peak vanishes into the darkness of space itself. A structure so immense that it pierces through the atmosphere, through the clouds, through the very boundary between Earth and the cosmos. Now imagine stepping into an elevator at the bottom of this tower, pressing a button, and riding smoothly upward for days until you find yourself floating among the stars. No rocket necessary, no explosion of fuel, no violent thrust against gravity's grip. Sound like science fiction? It should. But here's the unsettling truth. The physics that would make this possible are not only real, they're being studied right now by some of the brightest minds on our planet. The question isn't whether a space elevator could work. The question is whether we have the courage, the resources, and the time to build one before our window of opportunity closes forever. What if I told you that everything you know about space travel might become obsolete within your lifetime? That the thundering rockets, the billowing clouds of fire, the astronomical costs of reaching orbit could all become relics of a primitive age? Right now, as you listen to this, engineers and physicists around the world are working on a technology so audacious, so seemingly impossible, that it makes the Apollo missions look simple by comparison. They're trying to build a stairway to heaven. And if they succeed, humanity will never be the same. Close your eyes for a moment and think about this. How much would you pay to go to space? Not as an astronaut, not after years of training, but as a passenger, as easily as you might board a train. What if the cost wasn't millions of dollars, but thousands? Or hundreds? What would that mean for our species? For you? For your children? These aren't idle questions. These are the stakes we're dealing with when we talk about space elevators. The concept sounds absurd until you understand the brutal economics of rocket-based spaceflight. Every single time we launch a satellite, every time we send supplies to the International Space Station, every time we dream of reaching Mars, we're fighting against the tyranny of the rocket equation. It costs approximately $10,000 to launch just 1 kilogram into low Earth orbit. 1 kilogram. That's about the weight of a laptop computer. Think about that. If you wanted to send yourself to space using current technology, at an average human weight of 70 kilograms, you're looking at $700,000 just in launch costs. And that's before you factor in the spacecraft, the life support, the training, the infrastructure. The economics are crushing. They've kept space exploration bottlenecked for more than 60 years. But what if there was another way? What if, instead of fighting gravity with chemical explosions, we could use physics itself as our ally? The story of the space elevator begins not in a laboratory or a government facility, but in the mind of a Russian scientist who was staring at a building. The year was 1895. More than 6 decades before humanity would even reach orbit. Konstantin Tsiolkovsky, the man who would later be called the father of astronautics, stood in Paris, gazing up at the newly constructed Eiffel Tower. At 300 meters tall, it was the tallest structure humanity had ever built, a monument to engineering ambition. But Tsiolkovsky's mind went further, much further. He imagined a tower that didn't stop at 300 meters. Or 3,000. He imagined a tower that reached all the way to space, to an altitude of 35,786 kilometers above the Earth's equator, to a point where an object orbiting our planet takes exactly 24 hours to complete one rotation. A point where it would hover motionless relative to the ground below. A geosynchronous orbit. Think about what Tsiolkovsky was proposing in 1895. The Wright brothers hadn't yet achieved powered flight. Einstein hadn't published his theory of relativity. The world still ran on steam and coal. And this Russian schoolteacher was imagining a structure tall enough to reach orbital altitude. It's almost laughable, except that the physics was sound. The mathematics worked. The only problem? The materials didn't exist. The strongest steel in the world couldn't support its own weight at a fraction of the necessary height. If you tried to build a tower to space using conventional materials, it would collapse under its own mass long before it escaped the atmosphere. So the idea languished. A beautiful dream. a mathematical curiosity. For nearly 70 years, the space elevator remained locked in the realm of imagination, appearing occasionally in science fiction stories but never seriously considered by engineers. Humanity reached for space the hard way instead, with rockets that were essentially controlled bombs, hurling payloads upward through sheer explosive force. Then, in 1960, something changed. Something that would rewrite the entire equation. A Russian engineer named Yuri Artsutinov was thinking about satellites. The Soviet Union had launched Sputnik just 3 years earlier, igniting the space race, and the limitations of rocket technology were already becoming apparent. Artsutinov asked himself a deceptively simple question. Instead of building a tower up from the Earth, what if we hung a cable down from space? The insight was revolutionary. Instead of a compression structure that would buckle under its own weight, imagine a tension structure, a cable anchored to a counterweight beyond geosynchronous orbit, held taut by centrifugal force as the Earth rotates. The physics are elegant, almost beautiful in their simplicity. At geosynchronous orbit, an object takes exactly 24 hours to orbit Earth, meaning it appears stationary relative to the ground. If you place a massive counterweight beyond this point, the centrifugal force of Earth's rotation will pull it outward, like a ball on a string being swung in a circle. That outward force could keep a cable stretched tight, reaching all the way down to the planet's surface. You wouldn't need to support the cable's weight from below. Gravity and rotation would do the work for you. Artsutinov published his idea in a Sunday supplement to the newspaper Komsomolskaya Pravda, not a scientific journal. A newspaper. The article was called "Into the Cosmos by Electric Train." It received little attention in the West. The space race was focused on rockets, on beating the Americans to the moon, on the spectacular and the immediate. A cable to space seemed too far-fetched, too distant, too slow. The idea independently resurfaced in 1966 when 4 American engineers, John Isaacs, Alan Vine, Hugh Bradner, and George Backus, published a paper in the journal Science titled "Satellite Elongation into a True Skyhook." They proposed essentially the same concept Artsutinov had described. A cable stretching from geosynchronous orbit to the Earth's surface, held in tension by the rotation of our planet. But still, the problem remained: materials. The cable would need to support not just its own weight but the weight of everything climbing up it. And the strength-to-weight ratio required was far beyond anything humanity could manufacture. Steel? Not even close. Titanium? Not strong enough. Diamond? Better, but still insufficient, and impossible to manufacture in the required quantities. The space elevator remained a dream. Until 1991. That was the year that Sumio Iijima, a Japanese physicist working for NEC Corporation, was examining the soot residue from experiments with carbon molecules using an electron microscope. What he discovered would change everything. He found structures unlike anything seen before. Tubes of carbon atoms arranged in a hexagonal lattice, incredibly small, just nanometers in diameter, but possessing properties that seemed to defy belief. They were called carbon nanotubes. Here's where the story becomes almost supernatural in its timing, as if the universe itself was conspiring to make space elevators possible. Carbon nanotubes, it turned out, had a tensile strength potentially 100 times greater than steel at 1/6 the weight. Let that sink in for a moment. 100 times stronger. 1/6 the weight. These microscopic structures, invisible to the naked eye, were theoretically strong enough to support their own weight at the heights required for a space elevator. For the first time in history, a material existed that could potentially make Tsiolkovsky's dream real. The space elevator community exploded with renewed interest. In 1999, NASA funded a workshop on space elevators. In 2000, Bradley Edwards, a physicist who had been working on advanced space tether concepts, published a detailed technical study that outlined how a space elevator could actually be built using carbon nanotube composites. The study was thorough. addressing everything from the cable design to the climbers that would ascend it, from the anchor point on Earth to the counterweight in space. Edwards estimated that a space elevator could be constructed for approximately $10 billion, a fraction of the cost of the International Space Station, and that once operational, it could reduce the cost of reaching orbit from $10,000 per kilogram to as little as $200 per kilogram. $200 to reach space. Do you understand what that means? At that price point, space doesn't belong to governments and billionaires anymore. It belongs to universities, to companies, to researchers and adventurers and dreamers. At that price point, we're not talking about a handful of astronauts visiting space in their lifetimes. We're talking about millions of people, industries, settlements, a true spacefaring civilization. But before we get carried away with utopian visions, we need to confront the staggering challenges that stand between us and a functioning space elevator. Because make no mistake, this is perhaps the most difficult engineering project humanity has ever contemplated. And the obstacles aren't just technical. Let's start with the cable itself. The theoretical strength of individual carbon nanotubes is extraordinary, yes. But there's a problem. A massive, frustrating problem that has haunted researchers for more than 2 decades. We can't manufacture carbon nanotubes at the lengths required. The longest continuous carbon nanotube ever created, as of the most recent research, measured about half a meter. Half a meter. We need a cable 35,786 kilometers long. That's not a gap in capability. That's a chasm. The current approach involves creating composite materials, weaving together millions or billions of shorter nanotubes into cables and ribbons. But every joint, every connection point, every place where one nanotube ends and another begins represents a potential weakness. The strength of the composite is nowhere near the theoretical strength of a single, continuous nanotube. Recent tests have shown that carbon nanotube composites achieve only a fraction of the theoretical maximum strength, somewhere between 1% and 5%. That's still impressive by conventional standards, but it's not clear if it's enough. The calculations are razor thin. The safety margins are terrifyingly small. Ask yourself this: would you trust your life to a cable where we're not entirely sure if it's strong enough? Would you step into an elevator and ride for 7 days up a ribbon of woven carbon, knowing that the math works on paper but that we've never tested anything remotely like it under real conditions? And that's just the cable. Let's talk about what happens at the bottom, at the anchor point on Earth's surface. The space elevator cable needs to be anchored at the equator. That's non-negotiable. The physics only work if the cable is positioned directly along Earth's rotational plane. The equator isn't exactly packed with stable, accessible locations owned by spacefaring nations. You're looking at either the Pacific Ocean, the Atlantic Ocean, the Indian Ocean, or narrow strips of land in South America, Africa, or Southeast Asia. Most proposals suggest a floating platform in the ocean, a massive mobile anchor that could move to avoid storms and could be positioned in international waters to simplify political complications. Imagine an offshore oil rig, but larger, much larger. This platform would need to withstand ocean currents, waves, and the tremendous forces transmitted through the cable from above. It would need to be permanently staffed, defended, and maintained. It would become one of the most valuable and vulnerable pieces of infrastructure on Earth. Which brings us to a terrifying question that nobody likes to discuss publicly but everyone thinks about. What happens if someone attacks a space elevator? The space elevator, if built, would instantly become the most critical and most fragile piece of infrastructure in human history. A single point of failure for access to space. Imagine the cable is severed, either through terrorism, warfare, or simple accident. What happens? The answer is cascading catastrophe on a scale difficult to comprehend. If the cable breaks near the ground, the upper portion, still anchored to the counterweight beyond geosynchronous orbit, would whip upward and away, pulled by centrifugal force. Tens of thousands of kilometers of cable would drift into various orbits, creating a debris field that could threaten satellites and spacecraft for decades. If the cable breaks at a higher altitude, say halfway up, the physics become even more nightmarish. The lower portion would fall back to Earth. But we're not talking about a simple vertical drop. The cable is in motion, rotating with the Earth. As it falls, it would wrap around the planet, a ribbon of carbon nanotubes moving at supersonic speeds, slicing through the atmosphere. The heat from atmospheric friction would be immense. The cable would likely burn up, creating a visible streak across the sky, raining debris across potentially thousands of kilometers. Anyone directly below would face danger from falling material. And the upper portion? Again, flung into space, a hazard to everything in orbit. The strategic implications are chilling. A space elevator would be a single point of failure, impossible to defend completely, vulnerable to attack from ground, air, sea, or even space itself. A well-placed projectile, a saboteur on the ground platform, a directed energy weapon, even a collision with space debris could potentially sever the cable. And unlike a damaged rocket launch facility, which can be rebuilt while other facilities continue operations, there's no redundancy with a space elevator. If it breaks, it's gone. Years or decades of work, destroyed in moments. This is why some engineers propose building multiple space elevators, distributed around the equator, providing redundancy and backup. But that multiplies the already astronomical costs and still doesn't solve the fundamental vulnerability. Others suggest military protection, exclusion zones, defense systems. But that raises another question. Who controls it? Who owns access to space? Think about the geopolitical implications for a moment. The nation or organization that builds and operates a space elevator would have unprecedented control over access to orbit. They could set prices, grant or deny access, determine what goes to space and what doesn't. That's power on a scale we've rarely seen in human history. It would make the control of oil resources look trivial by comparison. Would such power be used responsibly? Would it be used fairly? Or would it become a tool of dominance, a way to ensure that space belongs only to those who control the elevator? Some propose international governance, a space elevator managed by the United Nations or a coalition of nations, ensuring equal access for all humanity. It's a beautiful idea. It's also almost certainly naive. The cost of construction, the technical expertise required, the years of dedicated effort, these would likely come from a small number of wealthy nations or powerful corporations. Would they really surrender control once the elevator was operational? Would you, if you had spent billions of dollars and decades of effort to build humanity's gateway to the stars? Let's move beyond politics for a moment and talk about the experience of actually using a space elevator. Because if one is ever built, the journey would be unlike anything humanity has ever experienced. You arrive at the anchor platform, a structure floating in the ocean, or perhaps anchored on land near the equator. The air is hot and humid. The cable stretches upward, a ribbon too thin to see clearly with the naked eye at first. But as your eyes adjust, you catch glimpses of it, glinting in the sunlight, ascending into the sky until it simply vanishes into the blue. You're told the cable is roughly 1 meter wide but only a few millimeters thick, like a ribbon rather than a traditional rope. It needs to be wide to spread the load, but thin to minimize air resistance in the lower atmosphere. You board the climber, the vehicle that will carry you to space. It's not like any elevator you've ever seen. It's a sophisticated piece of machinery, probably powered by electricity transmitted through the cable itself or beamed up from the ground using lasers. The climber grips the cable, using friction or mechanical grippers to hold on while motors pull it upward. You settle into your seat. The door closes, and you begin to rise. At first, it doesn't feel dramatic. The climber accelerates smoothly, but not quickly. Maximum speed is limited by the strength of the cable and the efficiency of the motors. Most proposals suggest an average speed of around 200 kilometers per hour, fast by terrestrial standards, but painfully slow when you're traveling 35,000 kilometers. At that speed, the journey to geosynchronous orbit would take roughly 7 days. 7 days of continuous climbing. During the first few hours, you'd still be in the atmosphere, passing through the troposphere where weather happens, then into the stratosphere. You'd watch through the windows as the sky gradually darkens, transitioning from blue to deep indigo to black. The clouds would fall away below you. The curvature of the Earth would become visible. And you'd still only be a tiny fraction of the way to your destination. As you climb higher, air pressure drops. The climber would need to be pressurized, like an aircraft cabin. Around 12 kilometers up, you'd pass the altitude of commercial airliners. At 20 kilometers, you'd be higher than any airplane can fly, entering the realm of specialized research aircraft and weather balloons. At 50 kilometers, you'd reach the edge of what we traditionally consider the atmosphere. And you'd still have more than 35,000 kilometers to go. Around 100 kilometers altitude, you'd cross the Kármán line, the internationally recognized boundary of space. Out the window, the Earth would be a sphere now, unmistakably curved, stunningly beautiful against the blackness. Stars would be visible in the sky even during the day, no longer scattered by atmospheric particles. And you'd begin to feel lighter. This is one of the strangest and most wonderful aspects of the space elevator journey. Unlike a rocket launch, where you experience violent g-forces and then sudden weightlessness, the space elevator provides a gradual transition. As you climb, the effective gravity decreases. At geosynchronous orbit, you'd experience true weightlessness, not because there's no gravity, Earth's gravity is still significant at that altitude, but because you're in orbit. You're moving at exactly the right speed that centrifugal force balances gravitational pull. But if you keep going, climbing beyond geosynchronous orbit toward the counterweight, something remarkable happens. You'd start to experience centrifugal force in the outward direction. You'd feel pushed away from Earth, as if gravity had reversed. At the far end of the cable, at the counterweight perhaps 100,000 kilometers from Earth, you could experience Earth normal gravity again, but pointing outward, away from our planet. Step off the elevator there, and you wouldn't fall back to Earth. You'd drift away into deep space, already traveling faster than escape velocity. This means a space elevator isn't just a way to reach orbit. It's a way to launch spacecraft to the Moon, to Mars, to the asteroid belt, without using any fuel at all. A spacecraft released from the far end of a space elevator would already have tremendous velocity relative to Earth. It could reach the Moon in a fraction of the time a rocket-based mission requires. It could travel to Mars using minimal propellant. The space elevator doesn't just make Earth orbit accessible. It opens up the entire solar system. Can you imagine what that would mean? Picture a future where missions to Mars launch not from Earth's surface with massive rockets, but from the end of a space elevator, already moving at interplanetary speeds. Where mining operations in the asteroid belt are economically viable because the cost of sending equipment and returning materials has dropped by orders of magnitude. Where solar power satellites in geosynchronous orbit beam clean energy to Earth, built from materials launched cheaply up the elevator. Where orbital manufacturing takes advantage of microgravity and unlimited solar energy to produce materials impossible to make on Earth's surface. Where tourism beyond the Kármán line isn't a million-dollar luxury for the ultra-wealthy but an achievable dream for ordinary people. This is the promise of the space elevator. This is why, despite the staggering challenges, researchers continue to work on the concept. Because if it can be built, it doesn't just improve space access. It transforms it. It takes humanity from being a species that occasionally visits space to one that lives and works there as a matter of routine. But let's be honest about where we actually are right now. Because the gap between vision and reality remains enormous. As of today, no one has manufactured a carbon nanotube cable anywhere near the length or strength required. The best composite materials we've created are promising but not sufficient. There are researchers working on alternatives: graphene ribbons, boron nitride nanotubes, other exotic materials. But all of them face similar challenges. We can create small samples with extraordinary properties. We can't yet scale up to industrial production of cables tens of thousands of kilometers long. There's also the problem of the climbers themselves. These vehicles would need to carry payloads of tons, climb for days continuously, and do so using power transmitted from the ground. The most common proposal involves beaming energy to the climber using lasers or microwaves. The climber would have panels to receive this energy and convert it to electricity for its motors. But this technology is in its infancy. Beaming significant power through the atmosphere with precision over long distances, tracking a moving target, doing so safely and efficiently, these are unsolved problems. And we haven't even discussed the construction process. How do you build a space elevator? You can't start at the ground and build upward. The cable can't support itself until the entire system is in place, counterweight and all. The most accepted proposal involves starting in space. You'd launch the counterweight and initial cable spool into geosynchronous orbit using conventional rockets. Then you'd simultaneously unspool cable in two directions, downward toward Earth and upward toward a higher orbit. As long as the center of mass stays at geosynchronous altitude, the system remains stable. The cable descends slowly over months, eventually reaching Earth's surface where it can be anchored. Meanwhile, the upward extending portion reaches farther into space, with additional mass added at the far end to serve as the counterweight. This process would require extraordinary precision. The cable would need to be unspooled at exactly the right rate, kept under the right tension, protected from damage. During the construction phase, the incomplete cable would be vulnerable to weather, space debris, micrometeorite impacts, and satellite collisions. The entire operation would likely take years. And if anything went wrong during construction, if the cable broke or tangled or drifted off course, you'd potentially lose the entire investment and have to start over. The cost estimates for all of this vary wildly depending on who's doing the calculating and what assumptions they make. Bradley Edwards' early 2000s estimate of $10 billion was based on assumptions about carbon nanotube manufacturing that turned out to be overly optimistic. More recent analyses suggest figures anywhere from $20 billion to over $100 billion. That's assuming no major setbacks, no technological dead ends, no cost overruns. Anyone familiar with large-scale engineering projects knows how laughably rare it is for something to come in on budget, especially when it's never been done before. For comparison, the International Space Station, a modular orbital platform constructed over decades, cost approximately $150 billion. The Apollo program, adjusted for inflation, cost about $250 billion. A space elevator would be a project of similar scale and cost, but with even more uncertainty because we've never built anything remotely like it. So why bother? If it's this difficult, this expensive, this uncertain, why not stick with rockets? Especially now, when companies like SpaceX are dramatically reducing launch costs through reusable rocket technology. The Falcon 9 can launch payloads for a fraction of what it cost a decade ago. Starship, if successful, promises to reduce costs further still. Maybe we don't need a space elevator. Maybe rockets, perfected and reused, are good enough. This is a legitimate question, and it's one that space elevator advocates have to answer honestly. The truth is that reusable rockets are indeed making space more accessible. The cost per kilogram to orbit has dropped significantly, but there are fundamental limits to how far rocket technology can go. The rocket equation is unforgiving. You need fuel to lift your payload, but fuel has weight, so you need more fuel to lift that fuel. And more fuel to lift that fuel. It's exponential. No matter how efficiently you design a rocket, no matter how many times you reuse it, you're still fighting this equation. Chemical rockets, by the laws of physics, can only become so efficient. A space elevator doesn't fight the rocket equation. It bypasses it entirely. Once the elevator is built, the marginal cost of sending something to orbit is primarily just the electricity to run the climber. That's it. No propellant. No massive infrastructure to manufacture and store rocket fuel. No violent launches that stress the payload. No risks of catastrophic explosion. Just steady, reliable, routine access to space. Think of it like the difference between using a ferry to cross a river versus building a bridge. Sure, you can make ferries more efficient, faster, cheaper to operate. But a bridge, once built, changes the entire equation. It makes crossing the river so routine, so effortless, that it ceases to be a significant barrier. That's what a space elevator could do for the boundary between Earth and space. But there's another factor, one that's rarely discussed in technical papers but might be the most important consideration of all: time. We may not have unlimited time to make this decision. The space around Earth is becoming increasingly crowded. There are thousands of active satellites in orbit, and tens of thousands more are planned in the coming decades. SpaceX alone plans to deploy tens of thousands of Starlink satellites. Other companies and nations are pursuing similar mega constellations. Add to this the debris from past collisions and explosions, and low Earth orbit is becoming a hazardous environment. This is the Kessler syndrome, proposed by NASA scientist Donald Kessler in 1978. The idea that at a certain density of objects in orbit, collisions become inevitable, each collision creating more debris, leading to more collisions, in a cascading effect that could eventually make certain orbital altitudes unusable. A space elevator cable would thread through the debris field of low Earth orbit. It would be a target, a static structure in an environment full of objects moving at kilometers per second. Even a small piece of debris hitting the cable could potentially damage or sever it. Proposals exist for making the cable mobile, able to shift slightly to avoid track debris, but we can't track everything. Objects smaller than about 10 centimeters are effectively invisible to our current tracking systems, yet they carry enough kinetic energy to be catastrophic if they hit a critical structure. The ironic nightmare scenario is this: the more we delay building a space elevator, the more satellites and debris we put into orbit with rockets. The more debris in orbit, the harder it becomes to build a space elevator safely. We may be approaching a window where the opportunity closes, where we've made low Earth orbit so crowded with our own technology that threading a cable through it becomes impossibly dangerous. If we wait too long, we might lock ourselves into rocket-based access permanently, not by choice but by consequence. This is speculation, of course. We don't know if we've reached that threshold or how close we might be, but it's a haunting thought. What if the space elevator was always a technology with an expiration date on its feasibility? What if we're living in the last generation that has a realistic chance to build one? Let me take you deeper into some of the more exotic proposals and alternatives that have emerged in recent years, because the classic Earth-based space elevator isn't the only concept on the table. Some researchers have proposed a lunar space elevator, a cable stretching from the moon's surface to a counterweight far beyond. The moon has much lower gravity than Earth, only about 1/6. This means the required cable strength is far less demanding. Materials that aren't strong enough for an Earth-based elevator would work fine for a lunar version. A lunar elevator could be built with Xylon or Spectra, advanced synthetic fibers that already exist and are commercially available. No need to wait for carbon nanotube breakthroughs. A lunar elevator would stretch from the surface to a point beyond the moon's L1 Lagrange point, the gravitational balance point between the moon and Earth. From there, payloads could be transferred to spacecraft with minimal energy. Mining operations on the moon could send materials to orbit efficiently. Spacecraft arriving from Earth could dock with the elevator rather than landing on the surface, saving fuel. The catch: you need to establish significant infrastructure on the moon first. You need a reason to build a lunar elevator, which means you need lunar industry, lunar bases, regular traffic to and from the moon. We're not there yet. But if humanity seriously pursues lunar colonization or lunar resource extraction, a lunar space elevator might be one of the earlier megaprojects, not one of the later ones. Then there's the Mars elevator concept. Mars has about 38% of Earth's gravity, higher than the Moon but far less than Earth. A Martian space elevator is more feasible than an Earth one with current materials, though still challenging. The counterweight would need to be positioned at the Martian equivalent of geosynchronous orbit, called geostationary orbit, roughly 17,000 kilometers above the surface. Again, the same logic applies. This becomes attractive once there's significant activity on Mars, once we're sending enough payloads to and from the surface that rocket-based access becomes a bottleneck. Some theorists have proposed truly wild variations. A rotating skyhook, for instance, which isn't anchored to the ground at all. Imagine a long cable in orbit, spinning end over end. At the lowest point of its rotation, one end of the cable dips down into the upper atmosphere, moving slowly relative to the ground despite its orbital velocity. A high-altitude aircraft or suborbital rocket could rendezvous with this slow-moving end and grapple onto it. The cable then carries the payload upward and releases it at a higher point in the rotation, adding velocity and altitude. It is not a true space elevator, but it's a middle ground, a way to use a tether to assist in reaching orbit without needing a structure all the way to the ground. The challenges with a rotating skyhook are considerable. The cable still needs to be incredibly strong. The rotation needs to be precisely controlled. The rendezvous with the moving end would be a complex, dangerous operation. But it sidesteps some of the problems of a traditional elevator, particularly the vulnerability of a ground anchor and the need to thread a cable through low Earth orbit debris. There's also the concept of a partial space elevator, sometimes called a mid-space elevator. Instead of stretching all the way to geosynchronous orbit, this cable would extend from a lower orbit down toward Earth, perhaps reaching an altitude of a few hundred kilometers. It wouldn't touch the ground, but it could lower the altitude that rockets need to reach, reducing the delta-V required and thus the fuel and cost. A rocket would launch to the lower end of the cable, grapple on, and then be carried higher by climbers. It's less ambitious than a full elevator, but potentially more achievable with near-term materials. Each of these alternatives has advocates and critics. Each represents a different trade-off between ambition and feasibility, between capability and cost, and each, in its own way, hints at the fundamental challenge. We're trying to solve a problem that sits right at the edge of what's physically possible. A little bit further and it would be impossible. A little bit closer and it would be easy. We're balanced on a knife's edge. Now let's talk about some of the stranger risks, the ones that don't make it into the engineering specifications but keep researchers awake at night. Lightning. A cable stretching from the ocean to space would be the tallest lightning rod ever constructed. In equatorial regions, thunderstorms are frequent and intense. A lightning strike on the cable could deliver enormous energy. The cable would need to be designed to conduct electricity safely, channeling strikes harmlessly to ground or dissipating the energy. But what if a climber is attached when lightning strikes? What if the electrical systems of the climber are fried? There are solutions, probably. Insulation, grounding systems, perhaps suspending climber operations during storms. But it's another complexity, another risk. Atmospheric oscillations. The cable would stretch through the entire atmosphere, experiencing winds at every altitude. High-altitude jet streams can reach speeds over 300 kilometers per hour. These winds would push on the cable, causing it to vibrate and sway. The cable would never be perfectly vertical. It would curve, blown by the wind, held in a complex equilibrium between tension from above and pressure from the air around it. The dynamics are fiendishly complicated. Engineers would need to model how the cable responds to changing wind conditions, ensure it doesn't develop resonant vibrations that could build to destructive levels, and design climbers that can navigate a cable that's not straight. Van Allen radiation belts. These are regions of intense radiation trapped by Earth's magnetic field. stretching from about 1,000 to 60,000 kilometers altitude. Climbers passing through this region would be exposed to radiation levels far higher than anything experienced on Earth's surface or even in low Earth orbit. For cargo, this is mostly irrelevant. For human passengers, it's a significant danger. The climbers would need shielding, adding weight and complexity. Passengers would need to spend days passing through hazardous radiation zones. The exposure could be limited with proper shielding, but it can't be eliminated. Anyone riding a space elevator to geosynchronous orbit would receive a radiation dose requiring careful monitoring and limiting the frequency of trips. Micrometeorites and space debris. We've mentioned this before, but it's worth emphasizing. Space is not empty. At orbital altitudes, there are countless tiny particles, both natural micrometeorites and man-made debris, traveling at velocities up to tens of kilometers per second. At those speeds, even a paint fleck carries the energy of a bullet. The cable would be thin, which is actually an advantage. It presents a small cross-section as a target. But over tens of thousands of kilometers and years of operation, impacts are statistically certain. The cable would need to be designed to withstand or self-heal minor damage. Perhaps a ribbon design with redundant strands, so that losing a few doesn't compromise the whole. Perhaps a coating that can seal small punctures. But every solution adds weight, complexity, and cost. And then there's the truly catastrophic scenario. What if something goes wrong with the counterweight? The counterweight at the far end of the cable is what keeps the whole system stable. It needs to be massive, probably thousands of tons. Some proposals suggest using a captured asteroid. Others propose constructing the counterweight from materials launched from Earth. Either way, it's a huge mass in space, held in position by the cable and by careful balance of forces. If the counterweight breaks loose, if the cable severs near the top, the entire lower portion of the elevator, no longer held taut, would fall back to Earth. The upper portion, the counterweight, would drift away into a higher orbit or potentially escape Earth's gravity entirely. Imagine witnessing that from the ground. A streak of light across the sky as tens of thousands of kilometers of cable descend, burning up in the atmosphere, wrapping partway around the planet. It would be visible from thousands of kilometers away. It would be one of the most dramatic and terrifying sights in human history. And the debris field left behind, both in the atmosphere and in orbit, would be catastrophic for space operations for years. This is why safety systems would be critical. Redundancy in the cable. Monitoring systems to detect damage or stress. Protocols to evacuate climbers and potentially to safely detach the cable if catastrophic failure is imminent. But can you really have a safe failure mode for a structure this size? Can you engineer a gentle way for a space elevator to fail? These questions don't have easy answers. Maybe they don't have answers at all. Maybe the truth is that a space elevator, if built, would represent an acceptable risk, a calculated gamble that the benefits outweigh the dangers. We accept risks in other mega projects. Bridges can collapse. Dams can fail. Nuclear plants can melt down. We build them anyway, because the alternative is to never attempt anything difficult. But there's a difference between intellectual acceptance of risk and emotional comfort with it. Would you trust a space elevator? Would you send your child on one? Would you invest your life savings in a company that depends on one? These aren't technical questions. They're human ones. And they might determine the fate of the space elevator more than the engineering ever could. Let's shift now to the people who are actually working on this, because despite all the challenges, there are individuals and organizations dedicated to making the space elevator a reality. The International Space Elevator Consortium is a collection of researchers, engineers, and enthusiasts who organize conferences, publish studies, and advocate for space elevator development. They've produced roadmaps outlining the steps needed to achieve a working elevator, identifying key technological milestones and research priorities. In Japan, Obayashi Corporation, a major construction company, made headlines in 2012 by announcing their intention to build a space elevator by 2050. They've continued to invest in research, particularly in carbon nanotube production and climber technology. Whether they'll meet their ambitious timeline is doubtful, but the fact that a major corporation is seriously pursuing this lends credibility to the concept. There have been competitions, too. The NASA-sponsored Space Elevator Games ran from 2005 to 2009, offering prizes for advances in climber technology and tether materials. Teams competed to build climbers that could ascend a cable as quickly and efficiently as possible, powered by lasers beamed from the ground. The competitions drove innovation and proved certain concepts, though the cables used were only a kilometer or so long, nothing like the real thing. University research groups around the world are working on pieces of the puzzle. Materials scientists are pushing the boundaries of carbon nanotube synthesis. Aerospace engineers are designing climber mechanisms. Physicists are modeling the dynamics of ultra-long cables in orbit. No single group is building a space elevator, but collectively, they're advancing the knowledge base, making it less impossible with each passing year. And then there are the private individuals, the dreamers who've made the space elevator their life's work. People like Brad Edwards, who left a comfortable position in mainstream aerospace to focus on space elevator research. Or Keith Lofstrom, who's proposed alternative concepts like the launch loop, a different approach to non-rocket space launch. These are people who've bet their careers on an idea that most of the world still considers fantasy. Are they visionaries or are they tilting at windmills? History will judge. But their dedication is undeniable. Now, here's a thought experiment for you. Suppose tomorrow, some breakthrough occurs. Maybe someone figures out how to synthesize continuous carbon nanotubes at length. Maybe a new material is discovered with even better properties. Maybe a wealthy nation or a coalition of nations decides that the strategic value of controlling space access justifies the cost and commits to building a space elevator as a national priority, the way the United States committed to reaching the moon in the 1960s. Suppose the decision is made, the resources are allocated, and construction begins. What then? How would the world change in the years during construction? The project would employ thousands of people directly and tens of thousands indirectly. Material science, power transmission, orbital mechanics, robotics, all these fields would see massive investment and rapid advancement. The anchor platform would become a hub of activity, a new kind of space center, not for launching rockets but for sending a steady stream of climbers upward. There would be setbacks. Almost certainly, there would be accidents. Maybe a climber falls during testing. Maybe a section of cable fails during construction. People might die. The public and political will to continue would be tested. Opponents would call it a boondoggle, a waste of resources that could be spent on problems here on Earth. Supporters would argue that it represents humanity's future, that the cost of not building it is stagnation. And then, maybe 10 years into construction, maybe 15, the cable reaches the ground. The system is complete. The first test climber ascends successfully. Then the first cargo. Then the first human passengers. The first successful round trip to geosynchronous orbit via space elevator. Can you imagine the moment? It would be a turning point in history as significant as the first moon landing. More so, perhaps, because unlike the moon landing, which was a singular achievement, the space elevator would be a permanent gateway, a fundamentally new capability. In the years following activation, the cost to orbit begins to drop. Satellites that were prohibitively expensive to launch become viable. Research that required expensive rocket launches becomes routine. Solar power satellite arrays start to be deployed, beaming clean energy to Earth. Manufacturing facilities in orbit produce materials and products impossible to make in gravity. Space tourism isn't just for the ultra-wealthy anymore. Middle-class people start saving up for a trip to space the way they might save for a luxury vacation. And then the second-order effects begin. With cheap access to orbit, mining near-Earth asteroids becomes economically feasible. A single metallic asteroid can contain more platinum group metals than have been mined in all of human history. Water ice from asteroids can be converted to rocket fuel in orbit, enabling deep space missions without the crippling cost of lifting fuel from Earth. Permanent space stations, no longer limited by launch costs, grow into space cities, hosting hundreds or thousands of people. Mars missions, instead of being once-in-a-generation spectacles, become regular occurrences. Ships assembled in orbit, fueled from asteroid resources, carrying supplies launched cheaply up the elevator. The Moon sees permanent bases, supplied via lunar elevators or regular shuttles from Earth. Humanity becomes a multi-planet species, not in some distant future, but within a single human lifetime. This is the optimistic vision. The space elevator as the key that unlocks the solar system. And it's not fantasy. It's a plausible consequence of dramatically reduced launch costs. We've seen this pattern before, throughout history. When transportation becomes cheaper, everything changes. The railroad transformed continents. The shipping container transformed global trade. The airplane shrank the world. The space elevator could do the same for the barrier between Earth and space. But let's be brutally honest about the other possibility. The pessimistic scenario. Suppose we build a space elevator and it doesn't work the way we hoped. Suppose the costs overrun so dramatically that only a handful of launches per year are economically viable, not enough to justify the investment. Suppose technical problems plague the system, climbers breaking down, cables requiring constant expensive repairs. Suppose a major accident occurs. Maybe the cable severs, maybe a climber falls, maybe dozens of people die, and public support evaporates. The elevator is abandoned, a monument to hubris, the biggest white elephant in history. The ruined cable drifts in orbit, a hazard to navigation, a reminder of failure. Or suppose it works, but the control of it becomes a source of conflict rather than cooperation. The nation or corporation that owns it uses their monopoly ruthlessly, charging exorbitant fees, denying access to rivals, militarizing space in ways that provoke an arms race. The dream of the space elevator opening the cosmos for all humanity curdles into a nightmare of exploitation and control. These dark scenarios are possible too. Technology is never inherently good or evil. It's a tool. The consequences depend on how we choose to use it, on the structures and values we build around it. A space elevator in the hands of a democratic, transparent, international coalition might be a force for incredible good. A space elevator controlled by an authoritarian regime or a profit-driven monopoly could be something else entirely. Which future do we get? We don't know. We can't know. But the possibility that we might have to make this choice, that a space elevator might actually be built in the coming decades, should make us think carefully about the world we want to live in and the principles we want to govern our expansion into space. There's another angle to this story that's often overlooked, the environmental impact. Rockets, for all their problems, are at least temporary. A few minutes of noise and pollution per launch, then it's over. A space elevator would be a permanent structure, a visible scar across the sky, a cable threading through the atmosphere and beyond. What would that do to our relationship with the heavens? For all of human history, the sky has been untouched by our hands. We've put satellites up there, yes, but they're invisible to the naked eye. The stars look the same as they did to our ancestors. A space elevator would change that. Looking up, you'd see it, a thin line stretching into the heavens, visible during the day as a glint in the sunlight, perhaps visible at night as well if it were illuminated. Some people would find it awe-inspiring, a symbol of human achievement. Others would find it disturbing, a violation of something sacred, the last frontier marked and claimed. And what about the wildlife? Migratory birds fly at altitudes where they could potentially encounter the cable. We're talking about a structure 1 meter wide stretching through the entire atmosphere. Would birds collide with it? Would it disrupt migration patterns? Studies would be needed, probably. Mitigation measures, perhaps lighting or radar systems to warn birds away. But every mitigation is another complexity, another cost. Then there's the question of atmospheric chemistry. The cable would interact with the atmosphere for thousands of kilometers. Oxygen, ozone, water vapor, all the complex chemistry happening in the different layers of the atmosphere. Would a cable affect any of this? Would it catalyze reactions? Would it disrupt the ozone layer? These sound like fringe concerns, but we've been surprised before by unintended consequences of technology. The scientists who developed CFCs didn't expect they would destroy stratospheric ozone. We'd need to study the potential impacts carefully before building something so massive and permanent. Let's talk about some of the myths and misconceptions that surround space elevators, because pop culture and misunderstanding have created a lot of confusion. Myth 1. A space elevator would lift you to the moon. Not true. Geosynchronous orbit, the destination for most space elevator designs, is about 36,000 kilometers up. The moon orbits at an average distance of 384,000 kilometers. They're not even close. A space elevator gets you to orbit, where the cost to go anywhere else becomes much cheaper, but it doesn't directly reach the moon or other celestial bodies. Myth 2. The trip would be instantaneous or very fast. Also not true. We're talking about a 7-day journey, roughly, to reach geosynchronous orbit. Speed is limited by the power you can transmit to the climber and the stresses the cable can withstand. It's faster than walking, but slower than flying. It's a marathon, not a sprint. Myth 3. If the cable breaks, it will wrap around the Earth like a whip and destroy cities. This one has just enough truth to be dangerous. Yes, a breaking cable would be catastrophic. Yes, debris would fall over a wide area. But the cable is thin and light enough that it would largely burn up in the atmosphere. It's not a solid steel whip. It's a ribbon of carbon fiber that would likely fragment and incinerate during descent. Still dangerous, still a disaster, but not a planet-destroying apocalypse. Myth 4. Space elevators are impossible because we don't have the materials. This is the closest to true, but it's more nuanced. We have materials that theoretically could work if we could manufacture them at the required scale and purity. The challenge isn't that the physics forbid it. The challenge is engineering and production. That's a huge challenge, yes, but it's different from fundamental impossibility. Understanding these distinctions matters because the space elevator concept is often dismissed based on misconceptions rather than actual limitations. It's hard enough as it is. We don't need to make it sound even harder by spreading myths. Now, let's explore some truly speculative territory. What if space elevators are just the beginning? What if they're the first step toward even more ambitious megastructures? Once you have one space elevator, building a second becomes easier. You can use the first to lift materials for the second. Then a third. A network of elevators around the equator, providing redundancy and increased capacity. And if you can build elevators, you can build other orbital structures. Imagine a ring around the Earth at geosynchronous altitude, a continuous structure encircling the planet, connected to the surface by multiple elevator cables. This is the concept of an orbital ring, proposed by various science fiction authors and speculative engineers. An orbital ring could host vast solar panel arrays, beaming power to Earth. It could support habitats housing millions of people. It could serve as a construction platform for interplanetary spacecraft. It's a megastructure on a scale that dwarfs anything humanity has ever built, but the physics are sound, and the space elevator would be the enabling technology that makes it conceivable. Go further still. Imagine humanity spreads through the solar system, establishing presence on multiple worlds. Each significant body could have its own elevator. Moon, Mars, perhaps even some of the larger asteroids or moons of the outer planets. These elevators become the threads of a transportation network connecting human civilization across millions of kilometers. Spacecraft hop from elevator to elevator, using the rotational energy of each world to boost their speed, traveling the solar system efficiently and economically. This is the vision that animates the most passionate space elevator advocates. They're not just thinking about one structure or one decade. They're thinking about the shape of human civilization for centuries to come. To them, the space elevator is the first domino. Knock it over, and everything else follows. Are they right? Maybe. Or maybe the space elevator will remain forever just out of reach. A beautiful idea that never quite crosses the threshold from possible to practical. Or maybe we'll find a different solution entirely. Some technology we haven't imagined yet that makes the whole concept obsolete before it's even built. Which brings us to the alternatives, the competitors to the space elevator concept. Because if the goal is cheap, routine access to space, there's more than one way to approach it. Reusable rockets, as we've mentioned, are already dropping costs. If SpaceX or another company achieves their goal of fully and rapidly reusable orbital rockets, launch costs could fall to a few $100s per kilogram, maybe lower. That's not as cheap as a space elevator, but it's cheap enough to enable a lot of the same applications. And rockets have the advantage that the technology is proven. We know how to build them. We're just making them better. Then there are more exotic propulsion concepts. Nuclear pulse propulsion, where you detonate nuclear bombs behind a spacecraft to push it forward. Absurdly dangerous and politically impossible, but theoretically very efficient for deep space travel. Or laser propulsion, where ground-based lasers push lightweight spacecraft by ablating propellant or even just using light pressure. Or space fountains, electromagnetic launch systems that hurl payloads to orbit using magnetic acceleration. Or orbital tethers that aren't anchored to the ground but catch payloads in flight and boost them to higher orbits. Each of these has advantages and disadvantages. Each has passionate advocates. The future of space access might not be one technology but a suite of them, each optimized for different applications. Maybe small urgent payloads go on fast rockets. Maybe bulk cargo goes up a space elevator. Maybe human passengers use hybrid systems for safety and comfort. There's no law that says we have to pick just one approach. But there's something uniquely compelling about the space elevator. Maybe it's the visual simplicity, the pure elegance of a cable reaching to the sky. Maybe it's the metaphor it represents, a bridge between Earth and the heavens, a permanent connection rather than a fleeting rocket exhaust. Maybe it's the audacity of it, the sheer ambition required to say, we're going to build a tower to space, and mean it literally. Think about the psychological impact of a space elevator. If you're standing anywhere near the equator, you could potentially see it, a thin line ascending into the sky. Every day, you'd be reminded that space is accessible, that there's a road leading up and out. Children would grow up pointing at it, asking when they could ride it. It would change our collective imagination, make space feel closer, more real, more attainable. A rocket launch is a spectacular event, but it's rare, brief, confined to specialized facilities. A space elevator would be a constant presence, a part of the landscape and the skyline. It would change how we think about our place in the universe. Or maybe it would have the opposite effect. Maybe familiarity would breed contempt or indifference. Maybe after the initial wonder wore off, people would stop noticing it. Just another piece of infrastructure, like a highway or a power line. Maybe the routine access to space would make it boring, strip away the magic and the mystery. Is that a loss or a gain? When space travel becomes as mundane as air travel, as common as taking a train, have we lost something precious or have we gained something more valuable? These are philosophical questions without clear answers. But they're worth asking because they get at the heart of what we want from space exploration. Is the goal to preserve the frontier, to keep space as a realm of danger and adventure and rare achievement? Or is the goal to settle the frontier, to make space safe and accessible and ordinary, a place where people live and work and raise families. The space elevator represents the latter vision. It's infrastructure, not adventure. It's the choice to make space normal. As we near the end of this exploration, let's return to the question we started with. Will space elevators end the age of rockets? The honest answer is that we don't know. We can't know. The future is genuinely uncertain. But we can say this: if a space elevator is ever built, if all the technical challenges are overcome and the political will is found and the economic case is made, then yes, rockets as the primary means of reaching orbit will likely become obsolete, at least for most purposes. They'll still exist for specialized applications, for rapid response, for trajectories that don't align with the elevator's location, for military purposes perhaps. But the bulk of routine space traffic would shift to the elevator, because the economics are simply too compelling to ignore. But that's a big if. The biggest if in modern aerospace engineering. The space elevator exists in a strange limbo, not quite impossible but not yet feasible, tantalizing researchers with its promise while stubbornly refusing to yield to current technology. Maybe the breakthrough will come next year. Maybe someone reading this will be the one to solve the materials problem, to figure out how to manufacture carbon nanotubes at the scale required. Maybe a new generation of scientists and engineers, growing up with the idea of space elevators as a known concept rather than a wild speculation, will bring fresh perspectives and new approaches that crack the problem. Or maybe it won't happen in our lifetimes. Maybe it will take another century of materials science advancement. Maybe it will never happen, because some limitation we haven't discovered yet will prove insurmountable, or because humanity will find a better path to the stars. But here's what we can say with certainty. The space elevator concept has already changed how we think about space access. It's forced us to confront the limitations of rocket technology, to imagine alternatives, to think bigger. Even if a space elevator is never built, the research pursuing it has advanced material science, power transmission, orbital mechanics, and dozens of other fields. The dream has value, even if it remains a dream. And there's a deeper truth here, one that goes beyond engineering and economics. Humans need grand projects. We need challenges that seem impossible, that demand the best of our ingenuity and cooperation and courage. We need goals that force us to transcend our limitations and reach for something greater. The pyramids, the Great Wall, the cathedrals of Europe, the moon landing. These weren't purely practical undertakings. They were statements of ambition, expressions of what humanity could achieve when we dared to think monumentally. A space elevator would be in that tradition. A project that takes decades, that requires international cooperation, that pushes the boundaries of what we can build. Whether it succeeds or fails, the attempt would be worthy. The attempt would be noble. The attempt would remind us that we are capable of more than we think. So where does that leave us? Standing here in the present, looking up at a sky that's still out of reach for most of us, wondering if that will always be true or if change is coming. The space elevator shimmers on the horizon of possibility, neither real nor entirely imaginary, waiting for us to decide if we're brave enough, clever enough, determined enough to make it real. Picture that moment again, the one we started with. Standing at the base of a tower that reaches to space. The cable stretching upward, vanishing into the blue. The climber waiting, door open, inviting you inside. All the engineering challenges solved. All the political obstacles overcome. All the economic calculations made. It's real. It's here. The elevator to space. Would you step inside? Would you trust it? Would you ride for 7 days up into the black, watching Earth fall away below you, feeling gravity gradually release its grip, emerging finally into the silence and vastness of space? Or would you hesitate, remembering all the things that could go wrong, all the unknowns, all the risks? This isn't just a question about space elevators. It's a question about what kind of species we want to be. The kind that stays safe, that accepts limitations, that builds only what we know for certain will work, or the kind that reaches, that risks, that builds towers to heaven and sees what happens. The space elevator doesn't exist yet, but the choice to build it or not to build it, that choice tells us who we are. It tells us what we believe about our future and our potential. It tells us whether we think the stars are meant to remain distant lights in the sky or whether we believe they're destinations, places we'll visit, worlds we'll walk on, homes for our descendants. The age of rockets has given us a toehold in space, a tenuous presence, spectacular but limited. The age of space elevators, if it comes, would give us something more, a permanent foothold, a highway to orbit, a bridge between worlds. The transition from one age to the next isn't guaranteed. It's not inevitable. It's a choice we have to make, collectively, as a civilization. And the clock is ticking. Not because we have a deadline, but because opportunities can close. Because the longer we wait, the more complicated the orbital environment becomes. Because the materials scientists working on this problem today won't be working forever. Because the political will and public interest that exists now might not exist in 20 years. This is our moment. This is our choice. Build the elevator, or don't. Reach for space in a new way, or continue with the old methods. Transform our relationship with the cosmos, or maintain the status quo. What will we decide? I don't know. You don't know. Maybe nobody knows yet. But the question is before us. The tower to space, waiting to be built or waiting to remain a dream. The choice is ours. And whichever path we take, whichever future we choose, will echo through the centuries to come. The end of rockets? Maybe. The beginning of something greater? Possibly. The defining project of the 21st century? It could be. Or it could be nothing. It could remain forever a beautiful idea, a tantalizing might have been, a road not taken. But isn't it extraordinary that we even have the choice? That we live in a time where building a tower to space is difficult but not impossible? That the laws of physics permit it, that materials exist that could enable it, that human knowledge has advanced to the point where we can seriously discuss it. 1,000 years ago, this conversation couldn't have happened. 100 years from now, it might be obsolete, the space elevator either built and operational or definitively proven impossible. But right now, in this moment, we're balanced on the knife's edge of possibility. And that's a privileged place to be. So when you look up at the sky tonight, imagine that line stretching upward. Imagine the climbers ascending, carrying cargo and people, making the journey that for all of human history has been impossible. Imagine Earth with a tether to the stars, a connection that makes the cosmos not a distant dream but a reachable destination. It's not real, not yet, maybe not ever, but it could be. And the fact that it could be, the fact that we can imagine it and engineer it and perhaps build it, that tells us something profound about who we are and what we can become. The space elevator stands at the intersection of physics and ambition, of mathematics and dreams. It's the most audacious infrastructure project ever conceived. It's humanity's declaration that the sky is not a limit but a doorway. And whether we build it or not, the fact that we've dared to envision it, to work toward it, to take seriously the idea of a stairway to heaven, that alone is a kind of triumph. That alone says something worth saying about the human spirit. The tower to space awaits. Not in some distant future, not in a science fiction story, but here, on the edge of the possible, waiting for us to be bold enough to build it. Will we? That's the question that will define us. And the answer, whatever it turns out to be, will shape the destiny of our species for generations to come.